So up next is Intelligent Brushstrokes. The authors are Dan Wexler and Gilles Desistre. And the presenter is Dan Wexler. He's the CXO of the 11ers.
Hi everyone. Thanks again, like Ann said, for sticking around for the last session here. You know, this is the normally prestigious session that is assigned to all image and non-photorealistic rendering talks at SIGGRAPH, and I know the diehards out there are well acquainted with that. I'm here today. My name is Dan Wexler, as Kurt said. Thank you, Kurt. And my partner and I, Gilles Desistre, have an intelligent brushstroke algorithm we'll be talking about. It's a non-photorealistic rendering technique for taking your photos and turning them into works of art. This is a little bit lighter weight than the last talk. I will be showing absolutely no formulas during this talk and quite a few just pictures. So hopefully it will be easy on the eyes and easy on the brain. To start with, I thought I'd go through some of the looks that we're trying to achieve with our algorithm. We have a fully automatic stroke-based rendering algorithm that we are using to achieve painterly results. We wanted to be able to represent a wide range of styles with curved brush strokes, with open regions that are textured and still maintain detail of the original artwork. As well as being able to have fully abstract results and somewhat more photorealistic results. Like most of the stroke-based rendering algorithms, we use a layered approach, and I'll go into some more detail about the actual algorithm, but today I'll probably be focusing entirely on just one part of the algorithm. I won't be discussing some of the more interesting elements, which I'm happy to talk about later. We do use a genetic search algorithm to help create styles. So here's a few different variations of one of the images that I have here. The algorithm itself has 20 or 30 different parameters that control the placement of the brush strokes, the number of layers that we have, the way that strokes are generated, and the way that they're composited together. Rather than providing sliders and individual controls for those, we felt it was easier to navigate the styles with the genetic search, where you just choose different variations to blend together and combine visually rather than numerically. Here's a slightly different style of the same photo, which has a more textured look to it, but it still retains some detail around the edges of the objects. Again, it's a fully automatic algorithm. There's no interactive adjustment other than blending styles on the overall image. We also really wanted to be able to achieve some of the more sparser kind of painting styles, and I'll talk a little bit about how our brush placement algorithm allows these types of styles to still maintain some of the original image characteristics. Here are some of the original photos compared to some stylistic variations of them. So here's a photo my friend took in Thailand, I think, and the photo, the glazed image of it. We really wanted to be able to have the clouds have some of the original fluffiness, but the detail retained in the image. We also really wanted to work hard to be able to retain fine details in the image. So there's a lot of fine details around the top of this temple and the trees, and the stylized view, while having a very different look, does maintain some of that original detail in the original image. The product's now been out for about 2 weeks, and we have a lot of people who are using it. This is some of the images from people who've used it. This is from Dina DeBry, one of the past SIGGRAPH chairs, and some of their friends of ours. One of the characteristics we wanted to be able to have was sort of a relief look. So we have some images that have very broad and consistent areas, and we wanted to be able to treat those and still bring out some of the edges. In fact, the algorithm is particularly good at up-resing images, so we can take images of pretty low resolution and apply the stroke-based technique to it, and that's actually a really great way to raise the resolution of the image. I'll come back and talk about some of our image limitations actually at the end too. And for us, faces were really important to keep detail in, and we're particularly attuned as humans to facial features like eyes and mouths, and that's what I'll be talking about in the remainder of the talk. And for us, faces are not just humans. So here's the sort of meat of the talk. I'll be talking about guiding our stroke-based rendering algorithm using a probability density function to do non-uniform placement of the brush strokes. And we'll guide that PDF using facial recognition, which really helps us preserve some of those facial details. I'll start with just a really brief recap of stroke-based rendering algorithms in general and where our algorithm comes from. And I'll talk a little bit about how our algorithm has moved more of that calculation to the GPU than previous algorithms. Then I'll go through the placement algorithm itself, the non-uniform placement algorithm, which comes from some global illumination literature. And I'll talk a little bit about the types of PDFs that we use to drive the algorithm. So traditional stroke-based rendering, here are some images from previous SIGGRAPH papers. In the upper left, we have some of the work from Aaron Hertzman, which came out in the 90s. My personal work in this area started much earlier than that at Chaos Tools, which also had some very early work on stroke-based rendering and on genetic search algorithms. Aaron also did some work in the lower left that had this relief, this thickness of the strokes that's done through a shading algorithm. Both of his techniques were fully automatic, is my understanding, and he also did some work on curved brushstrokes and used layering to fill in the canvas. In fact, many of the algorithms intentionally place brushstrokes to try and make sure the entire canvas is covered with paint, and so they start with very thick strokes in layers underneath, and then add detail as you go up higher in the image stack. That's great, but it's sort of a little too hard-coded for us. We wanted to be able to have a much wider range of styles, so we don't dictate any of that in the algorithm. We let the genetic search vary the stroke size and the placement at each level independently. In the upper right is work by, I'll try and get this right, Kung Zhen and Mingchen Cao from UCLA. That's a more interactive technique. So they run some fairly advanced image segmentation algorithms. They do graph cuts, and they use this cool thing called primal sketch, which segments the image into different regions, the people, the background, and so forth. And then they have an artist interactively assign semantic meaning to each of those regions. Once they have the semantic meaning, they can order it in depth and apply different styles to each of the areas. Almost all of the algorithms that do stroke-based rendering have a large stroke texture library. We do too. These ones came from my mom, who's a really great artist. And the algorithm that we've focused on is more of an acrylic gouache and oil style that we actually use in the algorithm now. But there's nothing that prevents us from also using pencils as well as chalk and watercolor techniques. And it's one of the areas that we're looking to expand. These stroke textures will be applied to the individual geometric strokes, which we treat as ribbons. We'll come to that next. So our pipeline is designed to be entirely run on the GPU. And when it is run entirely on the GPU, it can run at interactive rates, and we very much hope to extend the algorithm that currently applies to still images to moving images and actually run in real time. Unfortunately, the current generation of mobile hardware has some limitations. In particular, there's no vertex texturing, which makes it basically impossible to dynamically generate geometry based on results that were computed earlier on the GPU. So the two parts of our algorithm that still run on the GPU are the facial detection algorithms, which use the libraries that are provided by the iOS and Android platforms to do facial detection. It's really cool that they sort of just provide that for free. Those algorithms return fairly simple things. They just tell you 2 points for the eyes and a point for the mouth. And I'll show you how we take that information and use it later. The other part of our algorithm that has to run on the CPU is the generation of the stroke geometry. We generate tens of thousands of strokes, and that data that they're generated from is actually calculated on the GPU. So we start by taking the input image and computing an orientation field. You can think of it as a simple Sobel. It's slightly more sophisticated than that. We use a little bit of relaxation techniques to come up with a slightly smoother orientation field. And then that image, even though it starts out on the GPU, we have to read it back to the CPU. Then we generate the geometry dynamically. We render that geometry, and we render it to both a color and a height map. The height map accumulates the height of strokes as you render, and we'll use that at the end in a final pass where we do a full screen shading pass to get that thickness, that oily look to the paint with some specularity. After rendering each of the layers, we compute the difference between the current image that we have and the original source image. And that gives us a sort of a difference map. That's one of the kinds of images that we can use as our PDF to drive placements of the strokes so that we can add detail to regions that still are significantly different from the original image. And so how do we place these strokes? That's sort of the core of what I want to talk about today. That stroke placement, in order to be run on the GPU eventually, needs to have a particular type of algorithm. A lot of stroke placement algorithms involve global relaxation techniques or rejection-based sampling. Those are pretty tough to implement on a GPU. So I wanted an algorithm that allowed us to have a constant number. We say, I want 10,000 strokes, and to be able to place 10,000 strokes immediately and in a parallel way. So again, it's currently implemented on the CPU, but it's designed to be implemented on the GPU. So how did we do that? Okay, so I come from rendering. I don't usually do stroke-based rendering. And in rendering, there's some great global illumination literature for placing ray samples to area light sources, or in this case, an environment map. If you do that naively and uniformly, as most of the stroke-based algorithms do, you tend to end up with fairly noisy images like the Killaroo on the upper right. So if we uniformly sampled that environment map on the left with rays, and we rendered that, we'd get a fairly noisy image. If we do a non-uniform sampling, where we actually sample the bright areas in the image more densely, we can use the same number of samples to get a much smoother Killaroo in the lower right there. And so I said, okay, I know that's done. How do you do it? And I went and found this great, actually, my friend referred me to this wonderful literature from Matt Farr and Greg Humphreys as an addendum to their book. This particular algorithm is not in the book. It's an addendum. It's available online. It's called Infinite Area Light Source Sampling with Importance Sampling. And I'll cover exactly how it works right here. It's pretty simple. So first you bucketize the PDF into, in their case, luminance for each bucket. And then we compute prefix sums. So we compute a prefix sum, a two-dimensional prefix sum, essentially. First, we go through each column in the image, and we compute the prefix sum for each column. And that gives us a normalized sort of distribution over that column. Then we take all the columns and we collapse them down to a 1D function, which is also a prefix sum. And so the prefix sum essentially starts out, and we add up all the values as we go along the bottom until we get to the right, and then we normalize that whole thing. So then we take these prefix sums, which can be computed ahead of time, and we generate two uniform random numbers. We use the first random number to search in the 1D array to find out where that uniform random number lies in the prefix sum, the 1D prefix sum. That gives us the column. And then we just do that same search vertically. And that gives us a non-uniform set of samples. What does that look like? Okay, so if we have this image on the left, I don't know who that guy is. And we compute a Sobel algorithm, a Sobel filter of that, and take the magnitude of the Sobel. That gives us the bulk of those brighter areas in that image. And then for the facial detection, we take the 2 points for the eyes and the point for the mouth, and there's a little heuristic oval that I compute for each of those, and we slap that on top of the Sobel magnitude. And that's sort of a very common, it's one of our modes for generating PDFs. So if we compare what it looks like when you do sampling with this algorithm, on the left we have the uniform sampling, uniform random sampling. And on the right, you can see that there's more detail in the eyes, and more brush strokes in the eyes, and more point samples in the mouth area. And you can also see, if you look closely, it's a little hard to tell, but there's a lot more samples along the image edges where the Sobel magnitude is high. So for these samples, not only do we change the density, but we also change the size of the brush strokes. So we use smaller brush strokes and shorter brush strokes in these areas. And why do we do that? Because as humans, when we look at faces, if you were to actually use big, broad brush strokes in the eyes and the mouth, you tend to make people look demonic and evil, and it's not very appealing. So by doing this, we make the images much more aesthetically appealing. So here's some of the results. I'm not sure how well these things show up, but this is the same image just blown up. And you can see, if you look closely, in the hair and around the face, we use much larger, more abstract strokes. And in the eyes and in the mouth, we maintain the detail. In the first versions of these images, my mother really did not like how I looked. And after we changed the algorithm, it was much better. And you can see one of the nice things is you get the glasses. They sort of stand out. Here is a few more examples. We, again, maintain that detail. We also sort of get a little more outlining from the smaller strokes that we use around the eyes. Here's another example. Sometimes the facial recognition doesn't work. It's kind of cute. You usually don't even notice. So in addition to doing the facial recognition, we can also just use the Sobel magnitude. If you use the magnitude in its normal orientation, you end up placing many more strokes along image edges. This is a great way to get sort of a hand, sort of a sparse style, a hand-drawn style. There's a couple of variations of a sculpture from Burning Man. And what you can also do is you can use the inverse of the Sobel. In other words, in the open areas, you want to place more strokes. In those areas where the image gradient is small, you can actually have pretty interesting results. We essentially advect particles through a field in order to generate the strokes. And so normally we use the orientation field as that advection field, but we can also apply other forces. So in order to do cross-hatching, for instance, we vary the stroke direction and sort of add a constant force or a radially varying force in the open areas. And that tends to affect the shape of the strokes. So that's pretty much what I have here today. We do have a few ideas for where to go from here. We're definitely, of course, planning on moving the entire stroke generation to the hardware. And basically what we just need there is a little help from the Apple developers to actually implement the vertex texturing, which worked in iOS 4 but was removed in iOS 5. A little unfortunate. And we're actually going to improve the shading model so that full screen shading pass that we do at the end, right now is just a simple local illumination model. But there's a couple of neat little tricks you can play that give it a more artistic feel. Rather than just dimming the color, you can play with the hue and saturation in that shading model. So there's a few things we want to play with there. And currently the algorithm is limited in terms of the output resolution because these strokes are they can be very long and they can be global. And so it's very difficult to do a tiled-based solution. And so we're limited currently by the size of a texture. But we do have a way now that we figured out of doing tiled rendering, and that will allow us to do arbitrary resolution outputs. So in addition to my partner Gilles, I'd really like to thank a few people who helped us with the development of the application, Drew Ulbrich, Ken Pierce, and of course my mom. So that's it, and I'd be happy to take any questions. Thank you very much.
We have time for a few questions.
And you can play with the app afterwards. Thanks a lot, everyone.
So I've got a question.
Yeah.
The goal of this technique and other ones kind of like it seems to be to create a more painterly appearance to the artworks. How does one determine what looks painterly? For example, do you have intuition or looking at just lots of these kinds of paintings as their previous work on this kind of thing?
Well, aesthetic appeal is pretty hard to measure, and that's why we do provide a lot of different styles and let you explore that range. But one of the things that we're actually thinking of doing that I didn't mention here is to actually use the genetic algorithm to guide, to allow it to evolve. So, for instance, you could take a target image. If you have something where you have a result, say, of a famous painter that you want to achieve, if you can find a way to get the original image or some version of it, and then apply this algorithm and you let the genetic algorithm actually breed it, you could actually come up with something that is closer to a more traditional or a well-known artist. That would be one way to do it.
Sure.
Yeah.
So I'm just wondering if you let people directly manipulate the priority field,
Um,
so that
we-
you can sort of prioritize parts of the image by choice.
We definitely thought about it. So there's a couple of controls that we would provide if we did decide to do direct controls. I've tortured so many animators over the years with bad controls. I kind of tried hard to avoid that in this application. But you could definitely allow people to paint the PDF directly so they could place the brushstrokes. You could also, of course, provide them controls for those individual parameters. We'll do that at some point if people really wanted it. It's not hard to do. We just sort of didn't want to give people that kind of control initially, just because it can be overwhelming when you have like 30 or 40 controls.
Mm-hmm. I guess I was just thinking about it in terms of both in terms of if I look at the photo of you, I don't really care about the bricks.
You didn't really care
I don't
about
really care about the bricks.
Yeah, the bricks, right.
Right. But the algorithm does.
So other image processing operations can often easily be done before or after as well. I mean, I would sort of see this as one stage in a pipeline, and the goal here is not to make a full image editing program, so we would allow it to be easily transferred, perhaps, between different programs. That would be one way to do that.
Okay, great. Yeah, I was just thinking about how to make insurance commercials with it or something like that.
Yeah, thanks.
Hi there. I've got a question about a tiny detail. So the Sobel filter gives you a high response directly on the edge. Is this really where you want to place your brushstrokes? Don't you want to place them off edge so that you can get a good gradient?
Perhaps. We also have controls which blur the images and actually do those placement at different resolutions. And that's one way that you end up with strokes off the edge, is just by blurring the Sobel or actually blurring the original image or the lookups into the image. And those are all different parameters of the algorithm. That's one of those things, that's why we didn't really provide these direct controls. They're so complex. The interactions between the different parameters are like impossible for me to predict, and I wrote the algorithm. And so it was just easier to sort of say, oh, does it look right? Take this one over here and that one over here and blend them together. That's been the only way that I've found to actually control that part of the algorithm.
All right, thanks.
Sure, thanks.
Let's thank our speaker.